Dear students, let us continue our study in this paper, which is organic spectroscopy, and in this particular module we shall understand the advanced NMR techniques. After studying this module, you shall be able to determine the multiplicities of all the carbon in a molecule using a combination of 13C NMR, DPT and 2D NMR. You shall be able to know about the 2D NMR technique, and also you shall be able to compare between the 1D and 2D NMR. So, let us begin our study of this module, dear students. The advent of modern FT NMR instruments enabled us to study advanced NMR techniques. The computer, which is built into modern FT NMR instrument, is very versatile and helps us to develop more complex and more interesting pulse sequences. The pulses can be transmitted with different durations. A variety of times can be programmed into the sequences, and due to these pulse programs, nuclei exchange energy affect each other relaxation times. They may also encode information about the spin coupling from one nucleus to another. So, keeping this background in mind, an important pulse sequence in 13C NMR spectroscopy is employed in the experiment like distortion-less enhancement of polarization transfer, which is abbreviated as DEPT. Let me repeat, it is distortion-less enhancement of polarization transfer, that is DEPT. And this method has become an important technique or method to determine the number of hydrogen atoms which are attached to a given particular carbon atom. 2D NMR, that is two-dimensional NMR, is another advanced NMR technique. The 1H and 13C NMR spectrum is the all-time tool used by synthetic and biomolecular chemists to elucidate the structure of their products on daily basis. The increasing complexity of natural compounds and their synthetic analogues implies the use of some more recent 2D NMR techniques that we shall be studying in this module. So, let us begin with knowing more details about the DEPT, that is distortion-less enhancement of polarization transfer. The two principal features of DEPT spectra are increased sensitivity by a factor of 4 and the spectrum editing facility for 13C spectra. By a linear combination DEPT spectra and the normal 13C spectrum, the multiplicity of all the carbons in a molecule may be very easily determined. And this you can see as it is being given in this particular figure, as you can see here, that you can see here the normal 13C spectra and you can compare the same with the DEPT spectra, and you can see it has become more simpler as compared to the normal one. This technique has proven superior to other techniques in giving information about the attached protons reliably, efficiently and with very high selectivity. In these spectra, there is a proton-carbon polarization transfer which takes place. The polarization transfer is from a nucleus with a relatively larger gyromagnetic ratio to the one with a smaller. And if we talk about, there will be three types of DEPT spectra which can be recorded. They are noted by numbers. For example, DEPT 45 gives a positive 1 signal for any carbon with an attached proton. DEPT 90 spectrum shows only CH carbons, where the DEPT 135, that is 135, shows positive CH3 and CH and negative CH2 signals, and this you can see as they are being shown in this particular figure. For example, in DEPT 135 spectra of methanol, as you can see here, 7 signals are positive due to 4 CH groups and 3 methyl groups, whereas 3 signals for 3 CH2 groups are negative, as you can see in this figure. It is important to understand that the appearance of positive and negative signals can be reversed by phasing. So, it is necessary to have some way of determining whether the spectrum has been phased for CH2 positive or negative. The intensity for quaternary carbon in DEPT is 0, and hence they are practically invisible in the spectra, and that is the reason why the complexity is reduced and you get comparatively a simple spectra. And here you can clearly see that the normal spectra is showing these peaks for C, CH, CH2 and CH3, but in DEPT it is corresponding to CH, CH2 and CH3. In DEPT 90 it is only showing the CH, and in DEPT 35 it is showing for CH and CH3 as positive, but for CH2 it is showing the negative. So, easily you can then identify that what are the type of hydrogens which are attached to these carbons. Now, let us go to 2D NMR. A conventional NMR spectra is a 1D NMR spectra that we have already studied, and this, if we recall, is a plot of intensity against the frequency. This type of spectrum plot does not give complete information regarding the coupling nuclei HH or CH, etc. And there is a possibility to separate out the interactions among the carbon and hydrogens of the given sample compound. This helps in establishing the relation between the coupling nuclei, like which protons couple with which carbons or with protons. Now, this involves 2 axes designated for frequency, and hence it is named as 2-dimensional NMR, that is 2D NMR. In 2D NMR, both the axes X and Y have chemical shift scales, and the spectra are then plotted as a grid like a map. The information can be achieved by looking at the peaks in the grid and matching them to the axis. The values of coupling constants cannot be obtained using this method, but the fact that 2 resonances are coupled can give information about the interpretation of the spectra. The most important and widely studied 2D NMR is the correlation spectroscopy, either homonuclear or heteronuclear. The homonuclear proton-proton case is referred as COSY, COSY, and this you can see in this figure which is shown here. On the other hand, the heteronuclear carbon-proton correlation case is known as HETCOR, that is HETCOR, and this is being represented in this particular figure. As you can see, this is the HETCOR for 1-propanol. The proton-proton correlation spectroscopy, that is homonuclear COSY, it gives the proton NMR spectrum of any molecule along the x-axis and repeats it along the y-axis. The signals are repeated, and whenever a proton couples with another proton, this is given by the contour of an off-diagonal cross peak. For example, in the COSY, that is COSY of 1-propanol, as you can see here, the peak marked A indicates a coupling interaction between the hydrogen at 1.5 ppm and the hydrogen at 3.6 ppm. And this corresponds to the coupling of the CH2 group and the adjacent hydrogen on the CH2OH group in this particular molecule, that is 1-propanol. Similarly, look at the peak marked as B here. This indicates a coupling interaction between the hydrogen at 0.7 ppm and the hydrogen at 1.3 ppm, and this corresponds to the coupling of the CH2 and CH3 in the 1-propanol. And there are a second set of equivalent peaks also marked A and B on the other side of the diagonal, as you can see here. Now talking about het core, the carbon proton correlation spectroscopy, that is heteronuclear het core, it gives out the 13C spectra of any molecule along the x axis and the proton NMR spectra of any molecule along the y axis. So whenever a carbon couples with proton, this is given by the contour here. For example, you can see here in the het core of 1-propanol, the peak marked A indicates a coupling interaction between the hydrogen at 0.7 ppm and the carbon at 10 ppm, and this corresponds to the group CH3. Similarly, the peak marked B indicates a coupling interaction between the hydrogen at 1.3 ppm and carbon at 25 ppm, and this corresponds to the CH2 group. The peak marked C indicates a coupling interaction between the hydrogen at 3.6 ppm and the carbon at 65 ppm, and this, you can make it out now, corresponds to the CH2OH group. So after this 2D NMR, where we had Koji and het core, now let us move to comparison of 1D NMR and 2D NMR. The increase in complex nature of natural compounds and their synthetic analogues and biosynthetic pathways, they involve the use of some recent NMR techniques like 1D and 2D NMR techniques. The simple NMR spectra of these complex molecules contain large number of resonance lines which cannot be resolved by 1D NMR spectra. And the interpretation and understanding of the NMR spectra of these molecules requires correlations between different nuclei that are absolutely contained in 1D spectra but often difficult to extract. The multi-dimensional NMR spectrum, like 2D NMR, it provides increased resolution and correlations are easy to analyze. A 1D NMR spectra, if we talk about, has two dimensions. The x-axis corresponds to the frequency axis, whereas the chemical shift are given in ppm, and the y-axis corresponds to the intensity. On the other hand, if we compare it with a 2D NMR, the 2D NMR spectra contains two frequency axes. The intensities are presented in the third axis and therefore usually displayed as the contour plots. For a typical 2D NMR spectra, 1D NMR experiments are performed a number of times. For example, for a typical 2D of 1H Koji spectrum, usually a series of 5 and 2 1D spectra is recorded. Dear students, let us now summarize what we have learned in this module. We have studied about the advanced NMR techniques, which includes DEPT and 2D NMR. We studied that in DEPT, one can see a normal peak for every quaternary carbon and methylene carbon, and there is inverted peak for every methane and methyl carbon. In DEPT, one can tell whether the number of hydrogens which are attached to the carbon is even or odd. And using DEPT, by changing the pulse widths and delay times, separate spectra for methyl, methylene and methane carbons can be obtained. Then we also studied about the 2D NMR technique, and in the 2D NMR technique, we studied about the cozy, where it is the homonuclear proton-proton case which is referred as cozy, but if it is heteronuclear carbon-proton correlation case, then it is heterocore. And we studied how if the proton-proton correlation spectroscopy, that is cozy, it is obtained where the proton NMR spectra of one molecule is taken along the x-axis and it is repeated along the y-axis. But if we recall the heterocore, in heterocore we studied that it is the 13C NMR spectra of a molecule which is taken along the x-axis and its proton NMR spectra is taken along the y-axis. And all these 2D will be helping us to clearly identify the coupling between the HH or the CH which is taking place, and it will help us draw the structure or elucidate the structure of complex molecules very, very easily.